Hello everyone, my name is John Welsh and I'm a developer technology engineer of autonomous machines for NVIDIA, and today I'm going to tell you how you can accelerate image classification and object detection models sourced from the TensorFlow models repository for use on NVIDIA Jetson. So the first thing we're going to cover in this webinar is we're going to overview the TensorFlow models repository and the subset of that we'll be using to accelerate for use on Jetson. This includes image classification and object detection. Then we're not going to go through both workflows because they're pretty similar. So we're just going to cover creating an object detection data set. So you'll see how you can create a data set of your own that you could train using the TensorFlow models repository, and then we'll train that data set on a desktop machine or a server. And then at the end, we'll transfer that over to the Jetson and optimize it using NVIDIA Tensor RT for deployment on the Jetson. So the TensorFlow model repository, it's hosted at the link shown here below, contains many different models developed by researchers that are using TensorFlow. And we're only going to be using a subset of this. So this includes the image classification models, which is assigning a label to an image, and the object detection models, which is detecting different classes of objects and their location within the image. So the TensorFlow models repository for these two tasks also include utilities for creating data sets that you can train on, and then already developed training scripts that allow you to take model architecture that you specify and then train it for the data set that you create, or a data set that's already been created for you. So here we have open the TensorFlow models repository in GitHub, and the portion of this repository that we're going to use is located in the research directory. For image classification, you would go to the SLIM folder, and this contains documentation for preparing a data set and training or using a pre-trained model for image classification. For object detection, it's also located in the research folder, but under object detection. And in this README, you can find similar documentation for creating a data set, defining a model architecture, and then training for the object detection task. So the TensorFlow models repository covers creating a data set and training a model, and then you could execute that model as is on a desktop or the Jetson, but there are a lot of performance benefits that can actually be gained by formatting the model to ensure good device placement on the Jetson. So that means placing certain operations on the CPU and other operations on the GPU. And then also formatting the model so that it's optimized well with Tensor RT. So the code to do this isn't hosted by TensorFlow in the TensorFlow models repository, but in a separate project that we're providing under the NVIDIA Jetson GitHub account at the link shown below. So here we have open in GitHub the project mentioned in the previous slide, and this contains the code for formatting the model, as well as some benchmark timings that we took for several of the image classification and object detection models. And we also include Jupyter Notebook samples to easily execute the object detection and image classification models on the Jetson TX2. Before we can get started training our model, we need to install the object detection API on our desktop machine. To do this, you just need to follow the installation guide that's referenced in the README of the object detection API on GitHub. So this includes stuff like setting up TensorFlow for the GPU, installing the necessary Python packages, and other dependencies. And when you get to the point where you need to install protocol buffers, we recommend that you follow the manual protocol buffer installation, because you need to have protocol buffers at least 3.0, and Ubuntu ships with version 2.7. Once you've successfully installed the object detection API, you should be able to open up a Python interpreter and import the object detection package. So now that we've installed the object detection API, we can move forward with creating our data set. To do this, you can follow the documentation in the object detection API README called Bringing in Your Own Data Set. This documentation basically covers the process of converting your dataset from whatever format that you trained it in to a standard format that the object detection API expects. So you could read through this in order to convert your own dataset. But for the purposes of this webinar, we're going to be using a dataset conversion script that's already been created and contained in the object detection API. This conversion script is located in the dataset tools directory and is called create pet TF record. The script uses images and annotations from the Oxford PET dataset, and they include the link in a comment at the top here. The dataset includes the bounding box annotation for the faces of different pet breeds. To obtain the images of the dataset, you would download the dataset link here, and to obtain the annotations, you would download the ground truth data link here. The conversion script expects the images and annotations to be in the same directory, so we create a new directory named data. We download and extract the images and annotations into this directory. Once that's finished, you should see two directories named images and annotations under the data directory. Now that we've downloaded our dataset from the Oxford Pets website, we need to run the conversion script to create the TF records. Following the flags defined in the conversion script, we need to set the data directory flag to the directory that we just made containing the annotations and the images, and the output directory to another directory where we'll store the TF records. We also need to set the label map path to the prototext file that contains the class labels. This has already been created and is located in the Object Detection API folder under Data. We copy the pets label map prototext from the Object Detection directory into our local data directory. Then we'll create a new directory where we store the converted TF records. Finally, we run the conversion script setting the flags mentioned earlier. After this is finished, you should see several records in the records directory. That concludes creating your dataset for the object detection model. Obviously, these steps would be different if you're using your own dataset. The next step in the process is to configure and train your object detection model. There are many different model architectures that the object detection API supports, but we'll only cover the single shot detector because that's what we've evaluated on Jetson. Before we train our model, we need to define our object detection pipeline. This is done by creating a configuration file. There are sample configuration files located in the following folder. We'll start with the SSD Inception v2 pets config, which has already been configured for the task at hand. If you were to train for a different task, you would need to at least change the number of classes to the number of classes that your dataset contains. You would also need to set the train input reader to have the path that corresponds to the records that you created for your dataset, along with the label map path set to the label map prototext that you have for your dataset. These are already set in this configuration file for the pets records that we created because they're associated with the conversion scripts shown before. So all we need to do in this case is change the path to be configured to the records directory that we made earlier. Also, training usually converges more quickly if we start from a pre-trained model. By setting the fine-tune checkpoint parameter under the training config, we can start from a model that's already been trained for the MS COCO detection task. The pre-trained model must share the same model architecture as that which we specified in our configuration file. So we'll download the SSD Inception v2 model. We create a new directory called nets where we'll store all our models. Then we download the SSD Inception v2 model and extract it into that folder. After that's finished, your Nets directory should look as shown. We create a new directory for the model that we're going to be training. And then we copy the existing SSD Inception v2 pets config into that directory. In the config file, we modify the fine-tuned checkpoint path to be the path of the pre-trained model that we downloaded earlier. We'll use a path relative to the workspace directory because that's where we'll execute the training command. We also configure the path for the label map and the training records. Once we've finished edits to our configuration file, we can run the training script. The training script has several flags which you can configure. Minimally, you'll need to set the model directory, which is where we'll output the trained model. This is the directory that we created earlier in the Nets folder. You'll also need to set the pipeline config path, which is the path to the configuration file that we just edited. You can also configure the number of training steps and the number of evaluation steps, as well as some other parameters. We create a bash script to wrap this command that makes it a little easier to read and configure. Our final bash script looks as shown. We call the bash script to begin training our model. While the model's training, we can visualize progress using a tool in TensorFlow called TensorBoard. We launch TensorBoard using the command as shown. We then open our browser to the address shown when we launch TensorBoard. After some time, we'll see a Scalars tab appear where we can view various parameters relevant to training, such as the loss. After training is finished, we'll see that our mean average precision and recall have plateaued, along with the loss. We can even see an example output by the network compared against a ground truth example. That concludes our discussion on how to train an object detection model for a custom task using the TensorFlow Object Detection API. Now we could load this model on the Jetson as is to perform inference using TensorFlow, but there are often significant performance benefits if we optimize the model first using TensorRT. TensorRT is a neural network accelerator developed by NVIDIA. Once you've already trained your neural network and you're ready for deployment, you optimize it using TensorRT to reduce latency and increase throughput. With TensorRT, models are optimized using several methods. One of the simplest methods is using hardware-accelerated support for reduced precision operations, such as floating point 16 or integer 8. Another method is to restructure the graph to combine operations and reduce the number of kernel calls that are necessary to execute the graph. Because the overhead of launching kernels on the GPU is significant when compared to the overhead of executing the kernels, this can greatly reduce the runtime of the model. Other methods for optimizing the model include automatically selecting the best kernel to perform the operation, multi-stream execution, and dynamic tensor memory. As a developer, there are a few methods you can use to optimize your TensorFlow model with TensorRT. In this webinar, we'll be covering using TensorRT integration, which is a package inside of TensorFlow. The TensorRT package in TensorFlow works by analyzing your TensorFlow graph for operations that are supported by TensorRT. It then takes a subgraph of connected supported operations and performs TensorRT optimization to create a new operation, which is a TensorRT engine that gets inserted back into your TensorFlow graph. You then execute this optimized graph using the TensorFlow runtime as you would for your unoptimized graph. The benefit of this method is that you can easily realize the performance benefits of TensorRT without having to make any great modifications to your TensorFlow application. In addition, unsupported operations are easily handled because they're just run in native TensorFlow. If you were building an application to use native TensorRT, you would need to implement these operations as plugins. For some applications, especially those that you don't want to depend on the TensorFlow runtime, using the plugin method may be desired. Here we show the benefit of using TensorRT integration in TensorFlow to optimize image classification models. The optimized models are shown in green and the original models are shown in gray. We can see that the runtime of each model is reduced by about 4 times when using TensorRT integration. We also see significant performance improvements for the object detection task. The performance benefits may be slightly smaller than for image classification because a larger portion of the object detection model is not natively supported by TensorRT. Now that we've seen the performance benefits gained by optimizing our model using TensorRT integration in TensorFlow, we can run through the steps of optimizing our model with TensorRT. We could skip ahead to optimizing our TensorFlow model using TensorRT integration, but we've provided some scripts under the NVIDIA Jetson GitHub account that format the model to ensure good device placement and best optimization using TensorRT integration. This is specific to the models listed under the NVIDIA Jetson GitHub account. One of the operations that the model formatting scripts perform is replacing the unsupported ReLU 6 operation with a combination of other operations that are supported natively by TensorRT. By doing this, we can create a larger subsection of the graph that is supported by TensorRT, reducing the number of engines that we need to create. Also, we notice that some of the operations in the post-processing steps of the object detection model run on the CPU while others run on the GPU. This causes the network to copy data back and forth between the CPU and the GPU. By forcing all of the operations to occur only on the CPU, we can reduce the latency of the model. This is acceptable because the computational cost of each operation in the post-processing steps is relatively small compared to the cost of copying the data back and forth between the CPU and GPU. Before we can move forward with formatting our model, we need to install the GitHub repository mentioned in the previous slide on our Jetson TX2. To do this, we'll follow the setup instructions in the README. First, we'll assume you've flashed your Jetson TX2 using the latest Jetpack and have loaded the TensorRT software onto the TX2. Then, on the TX2, we install the following Python package dependencies. Next, we have to install TensorFlow on the Jetson TX2. Any version of TensorFlow past 1.7 should work provided that it's built with TensorRT support. We then clone the GitHub repository onto our Jetson TX2. We need to ensure that the recursive flag is set so that the TensorFlow model's GitHub repository is also cloned. Once that's finished, we change directories into the GitHub repository and run the installation script. After that's finished, you should be able to import the project in a Python interpreter. We've now finished installing the TFTRT models project, and we can move on with formatting our model. First, you'll have to copy the trained model over from the desktop machine to the Jetson TX2. We'll assume that you've created a new directory named nets under workspace and that you've copied the entire SSD Inception v2 pets directory into this folder. So after that's done, your directory structure should look like this. With the trained model on our Jetson TX2, we can now move forward with formatting the model and optimizing using TFTRT. To do this, we'll follow the example Jupyter Notebook in the TFTRT models GitHub project. First, we launch the Jupyter Notebook server from a terminal on our Jetson TX2. Then, in a browser, we navigate to the Jupyter Notebook server and open the Object Detection Example Notebook. The notebook uses the Inception v2 model trained for the MS COCO task. We'll need to update some of the parameters to use our newly trained model. First, we've already downloaded our models, so we don't need to include the portions of this notebook that download the pre-trained Inception v2 SSD for COCO model. So we'll just remove those. Next, we'll set the config file path to the absolute path of the configuration file for the model that we trained. We also set the checkpoint file path to the path of the trained model checkpoint from the last iteration in training. We also need to update the parameters in the build detection graph function to use the paths that we just set rather than the paths returned by the download detection model that we deleted. We'll then execute this block to call the build detection graph function. This takes in the object detection pipeline configuration file and a checkpoint containing the trained weights. It will then generate the TensorFlow graph, freeze it, and perform the formatting steps mentioned in the earlier slides. After we've generated the formatted frozen graph, we can call the TRT create inference graph function, which performs TensorRT optimization on the graph. We use the parameters shown here to optimize our graph with TensorRT. Because TensorRT optimization can take some time, you may want to serialize and save the optimized model to disk. You can execute this block shown here to do so. We then run the remaining code blocks to execute the optimized neural network on an example image. After that's finished, the results should look as shown. We can see the class label and probability of the detected breed shown in the bottom left corner of the green box. If we check the label map file, we can see that this detected identity is in fact the correct label. It's offset by 1 though because the detection is 0 indexed while the label map is 1 indexed. We've now run through all the steps necessary to create an object detection dataset, train a model starting from a pre-trained model, format the model, and optimize the model using TensorRT integration and TensorFlow. If you have any questions, we encourage you to bring them to either the NVIDIA Jetson developer forums, or you could even open an issue on the TF-TRT models GitHub project in the NVIDIA Jetson GitHub page. Thanks for your time.